So, today, probably till the end of the course, we're going to talk about the quantum electromagnetic field and about special interesting states that one can generate. And so, of course, you can think about many possible quantum states for the field, but we will focus primarily on states that we can prepare. So we are with the quantum field 2, and there will be quantum field 3 and 4. And what we are trying to focus on is, well, first, what we're going to finish today is operators, to understand the field operators and their relation to creation and annihilation, operators, and I mean we'll close this formal part of the definition. Then we will start discussing quantum states of light. And this is going to be an ongoing thing. We'll start with the simple things, and there would be like number states. They're also called Fock states. Which we mark N. We'll look specifically on this and give a specific look into what's a single photon and how do we know. And then we'll discuss the quantum photodetector. Okay, and after this, once we know this, we'll say something about, we'll make a pause and put here an intermediate, and that will be the quantum photodetector. And in relation to this, we will have the quantum coherence functions. Now then, and they're not going to be functions actually, they're going to be operators. Because every quantity, and why do we do this here? Because it relates to the properties of the single photon. I guess this will be our plan today. And later on, we will start to discuss next week, we'll start to discuss other quantum states, and specifically those that can be generated. To be honest here, to complete the Fock state, there will be a short discussion about phase states. Now then, the nice thing about these guys is that they're interesting theoretically and of no interest experimentally because there's no way to make them. But here there will be states like coherent states. I think you've seen them and heard about them. Alpha, that are the closest to classical field that there can be. They're the most classical. And then we'll talk about squeezed coherent states. And from this, we'll have a discussion about homodyne detection. Why are we going to talk about homodyne detection? Because this is the way we actually measure the field operators. This is the way we measure the quadratures. So x and p, or x and y, that we mentioned before, this is how we measure them. And it has to do with squeezing. We'll talk about parametric amplifiers that generate squeezing. So we have a lot on our hands. I guess this will not be today. But this is just to chart the way that we're going to tour. And there's one more. Let's see. I don't need that. Oh, that's better. So this is where we're going to. But just so you understand, yeah. Okay, so let's start. So let me remind you what our Hamiltonian is, or where we stopped. We said, look, this is not so good. I want a new tush. Is this one better? Ah. Yeah, seems so. So we're talking about the Hamiltonian of the field, the radiation. Let me remind you what we wrote last time. We started from Maxwell equations, and we quantized, and we decomposed as for modes, and we had this. Hamiltonian was sum over k and lambda. K are the possible wave vectors, lambda the polarization. We had here epsilon naught v omega k squared times ak lambda star plus, oh, we put a half in front just because here we artificially included this. And then we said, great, that's nice. Let's compare it. This looks, we know that each of those modes is a harmonic oscillator. Does it stand? Yeah, works. Good. Each of these modes is a harmonic oscillator. The quantum harmonic oscillator Hamiltonian would be h bar omega k times half, by the way, ak dagger ak. Well, of course, I'm looking at a specific mode here. So basically, there is a sum of, let's keep the sum over all modes. Each mode is a harmonic oscillator. So now, so we can identify, the analogy makes sense to identify these guys with these guys. Probably, let's do it the other way around so that. And now we can say that, so this is what we would like, and now we need just the prefactor. And that is that this, what's the relation between the operator for the vector potential A? So this mode A, you can say that, you know, this A k lambda equals what? Equals, yeah. I need to multiply by this and divide by this and have a square root. So it equals a what? Square root of epsilon v omega k divided by h bar. Did I get it right? No. I think that's fine. אתה צודק. Sometimes, you know, אני מצונן, אז מצליח לבלבל. Do we need שתיים too? Or maybe not. שתיים לא צריך. כן, נכון. Okay. And now we can say, look, this is this operator. But now okay. But now let me just remind you that basically this is the amplitude of a specific mode. So if I ask myself, what is A of R and T? Now here we should be careful. If you remember, now this is going to be an operator. But what about position and time? Are they operators? Surprisingly, the answer is not. They're not. They are the operators here, you know, and the fact that we call it position, and for the standard harmonic oscillator, you think about position as an operator, and there's position and momentum, but this position is not the one. Which is the position? That's the field itself. What oscillates? It's not, nothing oscillates, nothing spatially oscillates. There's no mass that moves in space. What changes in space is the field. At a specific point in space, the field is going up or down, but there's no real, there's no real spring or string that is vibrating there. So what I want to say is that, look, this is what? This is sum over all the modes. What? These functions, a, k of lambda of r and t. What are they? They are and of course, because it's a vector, then there needs to be the polarization vector. And those, we know what they are. We wrote them last time. They are these a, k, lambda of r and t are what? They are, well, there was this square root of h bar divided by epsilon naught v omega k times what? Times a k lambda e to the I k dot r minus omega kt. Was there an I outside? No. Plus its complex conjugate. But for the first time, let's just write it. A k lambda dagger e to the minus I k dot r minus omega kt. Close brackets. And the what?
There is a plus or no?
This is a plus. And this is a dagger.
Yeah.
Okay, let's put the plus here so it becomes clearer that it is there. And we need also the polarization. So we'll put here polarization, but that's now okay. And now, so this, or oh, we had here E here, so let's keep that. Let's not have a vector here and get rid of that one there, and so that we don't. So this is the field of a specific mode. And now you can see also, look, what do we have here? We have here A, annihilation operator, times a phase, plus a dagger times the conjugate phase. Depending on this phase, this operator can be either the position of that mode, because A plus a dagger is the position. So I can think of this as being a prefactor, I'll forget about it, A times e to the I chi, a phase, plus a dagger e to the minus I chi. And then this chi is a function. That's the only function of R and T. But at position and at specific space-time locations where this is 0, or of course 2 pi and so on, then this AK of lambda of R and T is what? It's the x quadrature, is A plus a dagger equals the x quadrature. So then it is position. And then you wait a quarter of a period. You give it some time for the phase to change, or you move in position by a quarter of a wavelength. And then this phase is pi over 2, 3 pi over 2, and so on. And then this A equals I outside, A minus A dagger, and then it is quadrature Y, or momentum. So here it is position, and here it is momentum. And everything is very general, and it varies between. So if you ask me where is the momentum and position, the word position is misleading here, because it is not space. It is not the coordinate in space. The equivalent of position that you know from the harmonic oscillator is the field, but the field at a specific time. And
position.
what?
And the field of position.
True. Position, this position is just a tag to tell you what I'm saying is that this is not just one operator. This is an infinite set of operators. For every point in space-time, there is the operator of the field at that point in space-time. And this operator at that point in space-time could be analogous to position, or could be analogous to momentum. And if you wait a quarter of a period, it will change from one to the other. For example, it tells you that the field does not commute with itself at different times or at different positions, because position and momentum don't commute. The field can be sometimes, so to say that, usually you can say, well, an operator always commutes with itself. Yes, if it is the same operator. But the field is not just one operator, it's an infinite set of operators. At every point in space-time, there's a different operator. And therefore the field operator, does it commute with the field operator? In which times? At the same time, yes. At intervals of exactly pi, yes. Pi or 2 pi or where it becomes x minus x, x minus x, then yes. But at other times, no. So the field at time t and the field at time t plus pi over 4 does not commute. And in general, it does not. Now, so far I was looking at the vector potential, but immediately I tell you, look, everything is the same. I can look at the electric field and I'll get the same understanding, and I look at the magnetic field and I'll get the same understanding. Why? Because what is the field? The electric field is this, the time derivative of A. So immediately I can write, without doing much, I can immediately write this for E. So I can write this function of E, K, and lambda, which is then, okay, what will there be here? I'm going to derive it according to time. So there's going to be a minus I omega k coming out, but there's a square root of omega k here. So I'll have the I outside. So this is minus I times square root of h bar omega k divided by epsilon naught v. So this, and everything else stays the same, almost. Here I'll have a k lambda e to the I k dot r minus omega kt. And now instead of plus, there will be a minus a k lambda dagger e to the minus I. I'll write here the same. There's no point in writing it again. Now, what happened? There's an I outside and there's a minus here. That's fine. That means that at the same time, when the vector potential, at the time when the vector potential is equivalent to position, and let's not continue to call it position, because position is misleading. Position is something that we remember from a harmonic oscillator. But let's forget about this. Let's call them quadratures. Okay? So there's the x quadrature and the y quadrature, or the x quadrature and the p quadrature. That's fine. Those are common names. But call them quadratures and not position and momentum. Okay? So at the same time, when the vector potential is equivalent to the x quadrature, the electric field at the same time is basically the same thing up to a constant multiplied by the y quadrature. But still, everything at that point in time, it's just like a phase shift. What about the magnetic field? Well, the magnetic field is also simple. And the magnetic field, that is the curl of A. So that is, we know this is k I k cross A. Or, yeah, I'll put it. So I can say, so from this we get that A k lambda, not A, sorry, B. And unfortunately, okay, I'll write it. That equals what? Let's see, we'll have I k cross. Yeah, if we'll need here to k, we'll have here is k cross ek lambda times the same thing. But there's going to be something about the frequency. Okay, I'll be a little bit more careful. K is what? This is omega divided by c. So we'll have basically the same thing, but there's going to be c squared downstairs. So we'll have this b k lambda just without the vector part. We'll have here I times square root of h bar omega k divided by c squared epsilon naught v times the same thing. Okay. Now, and you can see that if I want, I can absorb this I factor in the phase. So okay. So now yeah. Now let me go out for a moment and see if I can get a new marker so that we don't have problems. Let's see if there's somebody here. היי. אני רוצה טוש טוב. זה לא טוב. מה? נראה לי שלא, זה מה שנגמר בקצב גבוה. כן, יש שם איזה... כן, הם נועלים את זה כזה עם פלומבה. וואי, בראבו. Thank you. תודה. Okay. So, then, well now, so let's write things. So first of all, from now on, let's try to look. I don't want to, we understand what is happening. The electric field, or the magnetic field, or the vector potential are operators of creation and annihilation of photons. Photons are the quanta of energy of each harmonic oscillator, and each mode is a harmonic oscillator. Therefore, we now know what the photon is. We can define a photon. It is the quantum of energy in a single mode of the electromagnetic field. Notice there is no particle here. When we think of a particle, we think of something that is localized in space and time. There is, so okay, it's a wave packet and it's moving, but it has some classical limit of a localized body. There is no classical limit with a localized body of that thing. So to think about this as a particle of light, a small ball that moves at the speed of light, and somehow the wave is composed of all those tiny balls, it doesn't exist. There's no such thing. So to call a photon a light particle is wrong, just as calling a phonon a sound particle is wrong. There's no such thing. There's a sound quantum. If the waves are sound waves, they can carry sound quanta. But those are energy quanta. There is nothing localized about them. Now, we can make, now look, this is a quantum of energy in a single mode. We'll discuss this further soon. I can make localized modes. And then the photon would seem localized, but it would be only as localized as its mode is. I can make a classical wave packet. I can take classical waves, make a superposition of them, and have a wave that is localized. It starts and it ends. Now this wave can be considered a mode, maybe, in some concept. And this wave, this mode, can be occupied by a single photon. But there are limits to your ability to localize modes. Those are the limits of Fourier. You cannot make a field that is smaller than the wavelength of the light. I mean, you can make a pulse shorter and shorter and shorter, but it cannot be shorter than the wavelength of the light. And this is not so small. The wavelength of the light is a micron, half a micron, 2 microns. I can know where an electron is much better than a micron. I cannot, there is no meaning to saying, you know, I can try to localize a mode and then to say like I have a localized photon. No, you don't. You have a localized mode, and in that mode, there's no idea where that photon is, because that photon is not a particle, it's a quantum of energy in that mode. We'll discuss this a little bit more later when we will discuss single photons, but we can leave that for later. Yes, you had a question?
No, just if I'm understanding, so we have this mode.
Yes.
In this mode, there is a photon, and we don't know where is it. It's there, and this is it.
It's not just that there is a photon and I don't know where it is. There is no meaning to the question, where is the photon? It is in the mode. The mode is the photon, and just the amount of energy in that mode is what defines how many photons I have. But to ask, where is it? Is it really like bouncing in the speed of light? No, it's everywhere. It's the energy quantum that you have in there. And the electric field, or the magnetic field, or the vector potential, all that these guys do is they are both annihilation and creation operators. They are hermetic superpositions of creation and annihilation operators. So those are hermetic operators that can be measured. And as we said, all that they are is, or I can write, so let's just look at a specific mode of the field. So we said that Ek and lambda equals what? We had it here, minus I square root h bar omega k epsilon naught v. Yeah. Times ak e to the I chi minus ak dagger e to the minus I chi. And this chi is this k dot r minus omega t. And then, so I can call this, we just said that x equals a plus a dagger, and y equals a minus a dagger times I. So that means that I can make okay, I'll just write it. I mean, it's rather obvious, and you can check that it is correct. That if I want to express x as a function, if I want to express the field E as a function of x and y, then I'll write, where did my, the Machak disappeared? Aha. כן, המחק נאכל על ידי. Okay. So now if I can write that E of k and lambda, which is again an operator. Now, as we said, this is as a function of r and t. This equals also to this same I think we'll need a 2 outside. Immediately we'll find out. So I minus I over 2 square root times, and here we will have x k lambda cosine chi plus y sine. And as we said, this chi is k dot r minus omega k t. This is chi k lambda of r and t. And so that means that indeed, or you know what, let's just write it like that. I'll have the half out. And I write here x plus iy. Is that correct? No. Everything is almost correct. No, sorry. There's no I here because y absorbs the I here, and there probably will be an I outside. So this I stays. That one doesn't matter. Okay, so we can say that the field is composed of a cosine component and the sine component, and the cosine component is the x position or the x quadrature, and the sine component is the y quadrature, and those two, they do not commute because their commutation is 2i. Now I can make this in a more general way, the commutator of x k lambda with y k prime lambda prime equals 2i delta of k minus k prime lambda minus lambda prime. Or we don't need a minus even. I'll call it just delta of lambda and lambda prime. Just as I can say that, looks, the commutator of a k lambda and a dagger of k prime lambda prime is 1. So that equals delta of k minus k prime delta of lambda lambda prime. Yes, there was a question. Yeah.
Meaning to this? I mean,
what?
If they have the same wavelength, so they are.
Okay. So look, what does not commute? No. For example, let's think for a moment. It always helps to take a step back and think about harmonic oscillators. In a harmonic oscillator, what doesn't commute? The position and momentum of this oscillator. If I have two oscillators that are not related and independent, then the position of this oscillator definitely commute with the position or momentum of the other oscillator. It only does not commute with its own conjugate quantity, but not of other oscillators. Now what is written here? Between modes, the annihilation operator of mode k lambda, how does it commute with the creation operator of the other mode of another k prime lambda prime? And the answer is, as long as k and k prime are not the same, or lambda and lambda prime are not the same, then they commute, no problem. If they are the same mode, then they don't, and the commutation is 1. So, yep. Okay. So now, and then and it's easy using this relation. So now we know. No, why do I? No. And I can use this to ask, for example, what is for example, we can calculate the commutator of the field at time t1 with the field at time t2. Now let's do this for a specific mode. So I'm not going to carry again all the k and lambda. I assume that they are the same. What is this? So it's basically like saying, look, I want to calculate the commutator of E at point chi1 because that's what defines the location. This is this factor chi1 with the field at chi2. Well, what is it? Well, it's the commutator of what? I'll have here x cosine chi1 plus, there's all this I and everything outside, but I don't want to carry this, plus y sine chi1, commutator with what? X cosine chi2 plus y sine chi2. And what will this be? Well, you know, now I need to just write this. X cosine chi1 plus y sine chi1 times x cosine chi2 plus y sine chi2, everything minus what? The other way around. X cosine chi2 plus y sine chi2 multiplied by x cosine chi1. What?
This is the current function. I mean, it looks like the current function. It's very similar to this.
Good point. There is a strong relation, yes. We are going towards the coherence function will become a coherence operator, and it will relate to things that look like commutators. We'll see in a moment. Okay, so that's a very good point. Plus y sine chi1. Okay, and then you see, what do I have here? Well, there's going to be x cosine chi1 times x cosine chi2 minus x cosine chi2 times x cosine chi1. It's the same x, so this goes out. The only terms that remain are x cosine chi1 times y sine chi2 minus x cosine chi2 times y sine chi1. So I'm going to have here, there's going to be x y times cosine chi1 sine chi2. True? Yes. minus, let's see, cosine chi 2, y sine chi 1. And then there will be here minus what? Here we will have y first and then x. I'll have y times x times what? Basically the same thing. Y, sine chi 1 cosine chi 2 minus sine chi 2 cosine psi 1. Now basically it's the same thing up to a minus sign. Now what is this? This is the sine of chi. Let's see. Cosinus, sinus. Okay. This is the sine. Did we miss? There's something with the I. No. So yeah, okay. This is the sine of chi 2 minus chi 1. This is the same thing up to a minus sign, correct? This is minus sine of chi 2 minus chi 1. And this y times x is equal to x times y, and now something is I'm losing my mind. No, okay, I did something too quick, but what should come out is that this will be minus I divided by 2 sine of chi 2 minus chi 1. Now let's see, what did I miss? Was there something with the I that I forgot? Because it seems like I'm missing a sign somewhere. That this is the same up to a minus sign, and I don't like this minus. I would have liked it to be a plus. What did I do wrong? Does the I matter? No, it doesn't. It just comes out. So x plus y. So let's see, x cosine chi 1, y sine chi 2, minus x cosine chi 2, y sine chi 1. Sure. And then, not minus, plus. And then everything's fine. That was the problem. And then everything's fine. Yeah, then it will come out right. So what it will be, so then what we will have here is this sine of chi 2 minus chi 1 times what? Times the commutator of x and y. And this commutator is, as we said, 2i. Now, if you remember, there was the I outside doesn't matter. Does it? No, it doesn't matter. Now, what is important, the question of whether this is 2i or not, that is not important. What is important is to see that, look, the field at two different locations does not commute. It depends on the phase difference between those two positions, or two times. If the phase difference is such that the sign is 0, then yes, they commute. So you can measure the field if you know the field at a specific location in space-time, you know the field in that position after every half a period. That makes sense, because everything is periodic. So you know, if I know the field now, I definitely know it in 2 pi or 4 pi or 3 pi from now, because it's just the same up to a minus sign. So that should be. There shouldn't be a problem. If I know the field now, there shouldn't be any problem to know it after half a period. But there is a problem to know it after a quarter of a period, because then it is no longer the same. It's now what you see is not the x quadrature, now what you see is the y quadrature. They do not commute. So there is no reason. So, okay. That was about the commutator of the field. The time is, yeah, now I'm thinking, okay, so now, and just to remind you that if I think about a single mode of the electric field, just a reminder of how we can write the Hamiltonian. There are several ways to write the Hamiltonian of a specific mode. And that is, well, it was here a while ago. The Hamiltonian of mode k in lambda is what? Is h bar omega k in lambda times, well, I can write here ak lambda dagger ak lambda plus half. This part we know. Or I can write it as half h bar omega. I won't continue copying the k lambda, times a dagger a plus a dagger. Sometimes it's more convenient to use the symmetric form. Or I can write it as half h bar omega times x squared plus y squared. Meaning that, yeah, x is a plus a dagger squared plus, and not plus. Now y is I. So I'll have here, let's see, minus, yeah, minus a dagger squared. And then you'll see that everything goes away and you're left with these guys. Okay, and all those are convenient ways to write. Now let's start talking about the single photon a little bit, and about the quantum photodetector, which will take us to the quantum coherence functions. So if I think about a single mode of the electric field, of the EM field, we'll have a wave function. It doesn't have just an amplitude. We'll have a wave function. Just like, you know, the harmonic oscillator, it has a wave function. It can be in one of the Hermite-Gauss states. So there's a wave function, which can be composed, or you know what, before we write the wave function, let's write the basis. We can use the energy basis. This energy basis includes what? Nothing, the ground state, but this nothing is not zero. This is the Gaussian probability of being around x equals 0, which means around field equals 0. There is, so this is the vacuum. That's the Gaussian that we know. It has some, it's a Gaussian in x. What is x? X and y. It's a Gaussian in the quadratures. But it's not nothing. It's not just, that is important. And then there's what we would call a 1 photon, a 2 photon, and so on. Here has psi of x equals e to the minus x squared. I don't know, over 2, it doesn't matter. There's a, but what is this x? Or what does this represent? It represents the probability to find the quadrature x at a specific value. It's most likely to find it at the value of 0, but there is a probability of finding it at a value that is non-zero. It can either be positive or negative, that quadrature. So again, this is a Gaussian of what? This is a Gaussian of the probability to find a specific field. And in the vacuum, this probability is non-zero at fields that are non-zero. The average value that you will see is indeed quadrature equals 0. But it's not conceptually 0. Now what about this guy? Well, we know what it is. It has a psi, this is psi 0. This one has psi 1 of the same quadrature x, which is the polynomial h1 of x times e to the minus, no, not chi anymore. There's no chi. It's minus x squared over 2, or I can plot it as looking like this. It has Gaussian tails. What does it mean? It tells me, for example, that if I look at this quadrature x, I ask myself, what is the probability of finding the quadrature x at the value 0? Meaning that the field is not moving at all. The surprising answer is that then there is no probability to do this. If we ask ourselves, remind you what is in this case psi 1 of x squared, it looks like this. It's a double peak. So, and this is 0. So there's the probability of a single, being in a single photon state and finding no field at all, that probability is 0. But you could find, there is a region here where you could find the field anywhere within that, within this range of quadrature magnitudes. The quadrature x of a single photon can be positive, can be negative. I don't know. It can be anywhere between what you would call 0 and basically infinity, but it decays with the Gaussian tail, so very quickly disappears. So there's a range of possible quadrature values that I'll find. And I could find both the positive quadrature and negative quadrature. What about momentum? I don't know. I'm drawing this at the x position. So, you know, this is the states in the energy basis. And when I try to describe those states in the quadrature basis, and I have to select one quadrature as a function of x or y, I'll decide. And then I can calculate y, and so on. So in the energy basis, and if I ask myself, so a general state of the mode, just a single mode can have a zoo of possibilities. So there is here a superposition of sum over n, Cn, n. This is the most general mode you can write, of course, assuming that sum over Cn absolute value squared equals 1. Normalization. So this is the general state. Now, what do I mean? Look, these are waves. We already had superposition. Those are waves. Classical waves. There's no surprise in having a superposition of waves in classical electromagnetics. But those are superpositions of modes. If you remember, we wrote before, the electromagnetic field is equal to a sum over all modes with their amplitudes. This is a classical superposition. This is the classical superposition of different modes, and you could have, and they could be, I don't know, they could be interfering constructively somewhere and destructively somewhere. This was already there. So in that sum over modes that we wrote, all the classical interference was there already. But now there's a new superposition that didn't exist in the classical case. A single mode could have its amplitude in a superposition of possibilities. For example, it could be in a superposition of not vibrating, being at vacuum, or vibrating with exactly 1 photon, or vibrating with exactly 2 photons, or vibrating with 1,000,000. So this is something else. This is the fact that you could have a string, and the specific mode of that string could be in a quantum superposition within itself. This is something new. A new form of superposition, the fact that a single mode could be with interfering states of possible amplitudes. Now this is something that classically doesn't exist. A fact that the mode can be in a superposition of vibrating and not vibrating. This doesn't exist classically. So we have a new dimension of superpositions, which introduces a new dimension of complexity to the possibilities of what happens to the electric field. So this is where things are. So what we saw was, okay, so yeah, we met the vacuum, which clearly is not nothing. It is a state. It's a valid state. It has zero energy, but that's it. It's a valid state. And it has properties, and its properties affect the behavior, the physical properties of many things. We'll see slowly where. And we understood that the state of the mode, specific mode, K, is itself a superposition of the basis of its own. So I think that now is a good time to take a break and discuss the photodetector afterwards. So what time is it? Yeah, 5:20. So let's reconvene at 5:30. So yeah, unless you don't want to break, and the 5 of you can say something, but I think everybody at home already left. So yeah. What? כן.
אבל עכשיו אתה מציג אבל בסינגל מוד, אז זה בעצם פוטון עכשיו מה שיצא.
כן,
אמרת שהוא יכול כאילו, שהוא בעצמו כמות של פוטונים לפי האנרגיה בעצם.
נכון. תראה, כמו ש...
לא, אבל אם יש לו אנרגיה, אז הוא כן מספר מסוים של פוטונים. לא שאתה אומר, זה גם שיש שתי אופציות.
יש הרבה יותר משתי אופציות. אני יכול לדבר על, הנה, אני יכול לדבר על המצב, אני יכול לדבר על מצב קוונטי, שהוא מה? 1 חלקי שורש 2, ואקום פלוס 2. זה אומר שיש לי מוד של השדה האלקטרומגנטי, שלגביו כתבתי את זה. ובמוד הזה, okay, let's say it in English, because we're talking in English. So there is a mode of the electromagnetic field whose wave function is this, and this mode could be not vibrating, or vibrating with exactly 2 quantas of energy, and I don't know which. If I'll measure its energy, I could find 0, because it's not vibrating, or I could find 2. The probability of each one of them is half.
So you don't know nothing about the photon.
I didn't say anything about the photon. What I told you is that this mode is in a superposition of no photons or 2 photons. And it never has 1 photon, and it never has 3. So if I measure how many photons are in that mode, I could find only 2 possibilities in this case, either none or 2, and the probability of those 2 is half and half.
And if I'm measuring the wave function, so
you cannot measure the wave function.
Okay, the expectation value.
Okay.
So
I can ask, yeah.
Yeah, so the physical meaning of the place is I have an energy, and this energy is in this area. I mean, I'm assuming that I can measure this energy in this place.
So remember, what is, what did I mean? What does this position mean? It is this x. That means that I have a field. Every field has a cosine component and a sine component. I just don't know it. I can measure one of them. Okay? So I can try to measure the cosine component of the field. And I could get a number. We'll discuss soon how we do that. How do we measure? How do we really measure this cosine component or sine component of the field? It's called homodyne measurement. It was written on the board before. And when I measure this, I'll get possible values. It could be 0. It could be, I don't know, 1,000,000. It could be anywhere. There could be a set of values. It can be positive. It can be negative. So what's the probability, or specifically the probability density, of finding specific possible values of this x? And the answer is, if it's vacuum, then you'll have a Gaussian around 0. If it's a single photon, you'll have a double peak distribution around 0. So the average is still 0, but you could either find it at positive values around here or at negative values around there.
Of the possibilities of the x.
Right.
Okay.
So those are the probabilities of finding the x of the field. If it causes a headache, that's good. That's what it should. Okay, it says that the battery is low. Let's replace it. Any questions from home? יש שאלות שם בבית?
ראית את שבוע שעבר היית כבר על הערעור, גם עלו ציונים סופיים.
כן.
אנליטית. עכשיו באמת אני, דחית לי את הערעור, כתבתי לך על השאלות שטעיתי בהתחלה, ואז בעצם לשאר הנקודות לא בדיוק קיבלתי, כי אין מה לתת, כן?
כן.
לא, אבל עשיתי רק את המועד ב', אז כאילו מלא עוד שנה שעברה, היה את העבודה אחרי זו, כאילו היה שם פתרונות של הקורונה, והשנה נתקעתי ממש. כי אין לי את המועד, בהנדסה, אני עושה גם בהנדסה.
כן.
אז שם יש מועדי ג', כאילו קומבינה לכל האלה שנתקעו בחופפות וכאלה. ופה אין ממש פתרון. ומה, שנה הבאה אני אעשה, כאילו.
כעיקרון, בדרך כלל הפתרון הוא להיבחן... רגע, נכשלת לגמרי?
כן, ממש כאילו, 58 זה הסופי.
אתה רוצה לגרד חשוב לך לגרד את ה-60?
זהו, אני כן רוצה ציון טוב, השאלה בכלל מה האופציות, כאילו... אני יודע שבהנדסה זה מאוד קשוחים, אבל נגיד בקורונה נתנו לנו את המועדי ג' למי שהיה לו חופפים.
אז פה... רגע, יאשרו לך עוד מועד, אבל בדרך כלל יאשרו אותו בשנה הבאה.
כן, גם אני לא רוצה עכשיו שתכתוב משהו בשביל מחר, כן?
תראה, אתה יכול... כאילו, אפשר לנסות כזה... יש איזו סיבה, אתה ברגע האחרון של התואר או משהו כזה, זה יכול להיות שזה מה שמעכב לך את התואר? האם זה...
לא חושב.
אם אתה במצב כזה, אז אפשר לבקש בקשות מאוד מיוחדות. כלומר, אם אתה נמצא בסוף התואר ויש לך מבחן שמעכב לך...
אני לא בסוף, אני גם שנה הבאה, אבל אני אומר שנה הבאה, אני כאילו, כבר עשיתי את זה בקורס, וזה פשוט גרם לזה שעוד יותר, כאילו, פחות, גם לא הייתי בקורס, אז כאילו למדתי, גם לא...
כן.
אז כאילו, אני אומר מהשנה הבאה, כאילו, זה קצת כזה מאולץ.
That's the way things are done.
לא, אני לא מכיר את האופציות, כי אני גם לא...
כן.
לרוב אין לי מקרים כאלה.
רגע, אתה לומד פיזיקה הנדסה?
כן.
טוב. איך ציוניך בדברים האחרים?
לא, במבחנים אני מפקשש לפעמים, אז לפעמים יש את המועד ב', לפעמים זה...
בסדר, קורה.
אבל פה אין את המועד ב', זה הכישלון.
רגע, מה, כי פשוט לא יכולת לגשת למועד א'?
במועד א', שלחתי להם מייל, כאילו הודעתי להם על הרצון של החופפים, עכשיו בכלל לא ידעתי שיש, כאילו, חברים שלי שניסו, היו מהראשונים של החופפים, הראשונה שעברה בקורונה אמרו לנו שאין דבר כזה. אז באתי בתפיסה שאין דבר כזה. כאילו אמרתי, בטח אין. ואחרי זה חברים שלי אמרו שכן יש, והם נרשמו, והם כאילו חצי מהם ממש פתחו להם את הזום באמצע המבחן, כי כל מיני בלגנים. אז אמרתי, טוב, נשאל אותם בכלל אם יש. ענו לי באותו בוקר, זה לא שהייתי מוכן. זה היה ממש פישול.
כן.
עכשיו גם מה, אני אלך לצעוק שם על מזכירה של כאילו מה...
קצת קשה, נכון. טוב.
אין לי אפילו בעיה כאילו עוד לעשות, אם היה אופציה כמו מה שהשנה שעברה וכאלה.
לא, תראה, האופציה של שנה שעברה באמת הייתה ייחודית, ודרך אגב, הייתה גם לא טובה. כלומר, בדיעבד יש סיבה לזה שלא חזרנו על הדבר הזה, כי זה היה...
אילוצי קורונה, בסדר.
אילוצי קורונה בסדר, וגם אנחנו לומדים תוך כדי תנועה, וכשלומדים תוך כדי תנועה אפשר לעשות טעויות, וזאת הייתה טעות. כאילו, באופן מובהק. כי מה שקרה זה שאני קיבלתי 45 בחינות זהות. כאילו, זה היה מביך ממש. כאילו, היו כמה צדיקים שלא העתיקו, מדי פעם מצאתי כמה הפתעות מעניינות, כאילו, ואז אמרתי, אוקיי, פה יש מישהו שקצת חושב, לפעמים, כאילו, בדרך כלל זה היו כאלה שלא היו צריכים את ההעתקה, אבל זה היה מבחן של 24 שעות, ואחרי 24 שעות קיבלתי 45 בחינות, זה היה ממש כיף לקרוא 45 פעמים אותו דבר.
אני כל כך שמח שאין לי יותר מדי הצלחה בסמסטר קורונה, כי אז אפשר אחרי זה להגיד, זה סמסטר קורונה, מה זה שווה. לפחות הציונים שלי הם, כי בהנדסה על כל מבחן שהוא קצת פרנואיד למרצים, ומשום מה הם מאוד פרנואידים, אז פשוט לעשות את המבחן עוד יותר קשה. לעשות קשה זה לא בעיה, השאלה היא איך עושים מבחן נורמלי.
כן, תראה, זה נכון.
מועד א' אני ממש, כאילו אמרתי, הייתה שם שאלה אחת קשה, השאלה שהוא מסתובב, כאילו עוד משהו.
כן.
אבל השאר המבחן היה לא...
זה נורא סובייקטיבי מה שאמרת.
לא, מועד א' היה יותר קשה.
I'm sorry, I disagree. הממוצעים, לא היה הבדל כל כך גדול בממוצעים בין שני המועדים. אני אגיד לך מה כן ברור. מה שמאוד ברור זה שהסטודנטים מאוד, זאת אומרת, הזום קשה. כן. עכשיו, הוא קשה בעיקר בגלל חוסר ה... אם אתה מגיע לפה...
אז אתה מעיר אותי, אם אני זה זורקים.
בסדר, אבל לא רק זה, גם אין כל כך הרבה הפרעות. כאילו בבית כל כך קל. אוי, אני לא כל כך הצלחתי לעקוב, אני גם קצת רעב, ואח שלי בדיוק אמר משהו, וזה במילא מוקלט, אני אראה את זה אחר כך.
אצלי במבחנים היו פעמים שהניידת עברה בחוץ והפעילה ניידת שמחה כזה, כל מיני... וואי. גם לזה לא ממש התחשבו, אבל בסדר. כן. לי זה לא כזה מפריע, כאילו, במבחנים.
לא, וזה נכון שבאמת, כאילו... ההתפלגות... הגיע הזמן. אז שנייה אחת, אני רק אשטוף ידיים ונתחיל. Am I muted or not? Don't remember.
שכל פעם זה כזה, טוב, צריך להשלים את החומר, צריך להתכנס.
אני מנסה, אני כל דקה שאני בצבא, כאילו אני מביא חומר, אני מנסה, אתה יודע, לפעמים אין לי כוח הרבה.
אבל זה צחוקים, יש אווירה.
נכון, זה הקטע, אין לי באמת... אתה יודע, יש לך מלא שמדבר איתם, אז אתה כאילו מנסה ביד, ואתה רוצה לדבר, אתה מדבר איתנו שטויות, כאילו לא...
לא, אני תמיד מוצא משהו יותר חשוב לעשות, אבל...
אוקיי. Let's start. So, over the break, we mentioned like an example, which is to say that the state of a single electromagnetic mode could be in a superposition of vacuum, meaning non-vibrating, or at the zero level, or two photons. Of course, there could be many other possibilities of superpositions, and that means that I don't know what the energy of that mode is. Maybe it's not vibrating, maybe it is, and there's a superposition of those possibilities. So that's the added superposition, the quantum superposition. And to be honest, when you go, for example, for two modes, so this was, suppose that, if I have the quantum state of a single mode, what about the quantum state of two modes, if I have two modes? So two modes, for example, could be both in vacuum. Mode 1 could be in vacuum and the mode 2 can be in vacuum. But maybe also, I don't know, maybe 1 is at vacuum and mode 2 it has one photon. And generally, you could have n1 photons in mode 1 and n2 photons in mode 2. And those are the basis possibilities. But and the wave function, this is for single mode. 2 modes. So these are the bases, which is basically this n basis cross n of mode 1 cross with m in mode 2. You know this cross product of possibilities. I think this is something that you saw before. Yeah. And the mode, the wave function in this case, could be any sum over n1 and n2, c n1 and 2 times n1 in mode 1 and n2 in mode 2. You know what? Let's use n and m instead of so sum over n and m, c and m, n in mode 1 and m in mode 2. Or, and now as an example, things could be even more interesting because maximum use of the time. So I can have an example, the wave function of 2 modes as being, I don't know, 1 over square root of 2 times what? Vacuum, vacuum in 1 and 2. And, I don't know, 1 and 1. That means that I don't know how many photons are in mode 1. Maybe 0, maybe 1. I don't know how many photons are in mode 2. Maybe 0, maybe 1. With equal probabilities. But I do know that if mode 1 has 0 photons, so does mode 2. So either there's no photons in both of them, or there is a photon in both of them. But there never is one photon in one without a photon in the other. This is an entangled state of those 2 modes. This is something that is possible only quantum mechanically. The situation where I don't know, I have no idea what is the state of a specific mode, but there is perfect correlation between the modes. This is something that cannot happen classically. Classically, every mode has an amplitude. If this amplitude is correlated to the amplitude of another mode, then there is an amplitude and it is well defined, and both of them have the same amplitude. But now we can see a situation where a single mode is not defined. I don't know what happens in a single mode. Maybe there is no photons, maybe there's 1, maybe there's 2, maybe there's 1,000,000, I don't know. But I have some kind of a crazy superposition where whatever happens in mode 0, 1 happens in mode 2. Of course, I could put here more possibilities, I could generate other states, but this is the concept. So so there's a quantum superposition, and this is quantum entanglement. This is an entangled state. So those are the new possibilities that are open in quantum electrodynamics that couldn't exist in classical electrodynamics. And clearly, this entanglement explodes as the number of modes increases. Suppose that I restrict myself only to the states 0 and 1. So a single mode has two possibilities, either no photons or one photon. Okay, I restrict myself to this subspace. Of course, there are more possibilities, but let's just look at this. There's only 0 and 1. So a single mode has two possibilities, 0 and 1. Two modes have four possibilities, 0, 0, 1, 1, 0, 1, 1, 0. Three modes have 8 possibilities. Every time we multiply by 2. So this entanglement, the set of possibilities explodes as we go to more and more modes. This is why a quantum computer can do things that the classical computer cannot. Because a quantum computer can be in a superposition of classical possibilities, classical outcomes. And this superposition explodes as the number of modes in this case, or in the case of the quantum computer, qubits. A single qubit has two states, 0 and 1. Two qubits have four possible states, 0, 0, 1, 1, 0, 1, 1, 0. But those quantum mechanically can interfere. And 3 qubits have 8 possibilities, and all those could quantum mechanically interfere. And n qubits have 2 to the n possibilities, and all those could quantum mechanically interfere. Now, actually, in the case of the electromagnetic field, it is even much more, because the basis set itself is infinite. It's not just you have per mode 2 possibilities, you have per mode infinite possibilities, and now it's infinite to the power of n, which is the number of modes that you have. Okay. So, now let's remind ourselves something about the electric field that we mentioned. Now, I want to discuss the quantum photodetector. We discussed the classical photodetector. If you remember, we're going to do something, a little twist to understand what the quantum photodetector does. But before we do that, before we discuss the quantum photodetector, I want to prepare something, and that is to discuss what we call E plus and E minus, or E and E star, the analogies of E and E star. So if you remember, we mentioned that the electromagnetic field operates at position R, time t, equals what? Sum over all modes. There's a prefactor that we wrote before, and very quickly, I don't want to keep it. And then so there's I'll just write it like this to remember that there's a prefactor over there that we didn't write. Oh, you know what? No, but this prefactor is k dependent, so I can write here this prefactor in here that is multiplied by what? By a k lambda e to the I chi of r and t, chi k lambda, and I can write here, I'll write here plus. It was a minus, that part, whether it's a plus or a minus, that doesn't really matter. Either we have an I outside and there will be a minus here, or that we don't put an I outside and we put a plus here. It's just like absorbing a pi over 2 in chi. Okay? So I'll write here like this. Now, we can divide this. Normally we would say, look, I'll take the complex field. I'll define the field as being, classically we say that the field is we talk about the complex field. We say that, you know, that E of R and T is actually what the real field has some amplitude R and T times e to the I omega, well, T plus complex conjugate, right? Or this is just a single mode, maybe. So I have a sum over omegas, then I'll have here something which multiplies by the positive omega, and then there's another one that is multiplied by what? By the negative omega. So we're going to define quantum mechanically. There's also, you know, these are just playing with collections of operators. So now I'm going to collect all the positive frequency components. So let's say, now I'm going to say that this E R and T is composed of E plus of R and T plus E minus. Plus being all the positive frequency components or all the annihilation operators, and the minus being all the negative frequency components or the creation operators. So we could say, it wouldn't be correct, but we could say something like, look, this operator annihilates a photon at position R and T. It's a wrong statement. It's very attractive to think like it. It's almost correct, but it's not. But so I'm going to say this. Look, I'll call this would be E plus is a superposition of, superposition over k in lambda. Let's write here again h bar omega k divided by epsilon naught v square root times E, oh no, not E plus. This is, yeah, E plus of R and T. This is this times A k lambda e to the I. Now let's even write it, k dot R minus omega t. And what is E minus? Well, clearly I can write it again, but I don't really need it, because E minus of R and T is just E plus dagger. Complex. Now there is some confusion here that you should be aware of. It is common to write the annihilation operators as E plus. But plus and dagger looks very similar. And only the dagger part, the one that includes all the creation operators, is the one that is marked with a minus. Why? For no good reason, just to confuse you. And then we can see that E plus is a superposition of annihilation operators. So if E plus operates on a state, it will annihilate a photon. Where? I don't know. At some mode. So if I operate with E plus, so if I take this operator, E plus, and operate it on some state psi, what will it do? This will annihilate a photon, a single photon, from psi at an unknown mode, at some mode, what will I have? I'll have a superposition of annihilating either each one of those possible modes. And it will come with an amplitude, which is frequency dependent, and a phase. Now, by the way, this is the reason why we cannot say that this is an annihilation operator at position R and T. This thing that is not 1. Now, how do we compose, how do we make a delta function out of sine waves? A delta function is an equal superposition of all of them. So you know that delta of x equals sum over k e to the I kx, right? But that's the point. It's an equal with an equal probability here. This is not this weight. So this sum is not exactly, you know, I would like to say, look, there's like a delta function. So if I operate with this, it's like removing a photon at a specific location in space-time. It could be close to correct if the bandwidth here is limited. If you look at the limited bandwidth, so suppose that this is an optical frequency, so it's in the 10 to the 15 hertz or something, and there's a bandwidth around it which is not very wide. So then this prefactor is almost the same for all the possible frequencies in the... and then indeed, this will almost operate as if you're taking a photon in the region of R and T. But it will be just at some region around this point RT. But if you want to be exact, then you will say, no, I'll add more frequencies and more frequencies. And I'll be more exact on the time and on the position, and wrong. Eventually you'll fail, because when you try to make it smaller and smaller, specifically when you reach a single wavelength, then this thing breaks, because a single wavelength means that you have in this sum both something that is, I don't know, omega and twice omega. And you know, maybe you could say that 1 and 1.01 are almost the same numbers, but you cannot say that 1 and 2 are the same number. Okay. So now, and now let's say something about the when we think about coherence function. What time is it? Wake up. Okay. You guys at home have no questions at all? If you're there at all. Boom. Well, I don't know, maybe there was an alarm in there in the shelter. Today it could happen. Now, where were we? So, Okay. So now I want to discuss, after I defined these operators, I'll try to say something about the about the quantum photodetector. Now, what does a photodetector do? Photodetector, you put it in front of the light, it interacts with the light, it absorbs an energy quantum, transfers it into an electron and measures it. Now, we assume for now that we have photodetectors that, let's disregard the possibility of multiple detections. So again, if you remember, we were thinking about, we look a sufficiently short time where the probability of having 2 photoelectrons is negligible. So during a detection time, during detection time, this dt, what we have is 1 photoelectron. So a detection event is the detection of a single photoelectron. And we'll think about just 1. We don't discuss the possibility of 2 or 3. 1 photoelectron, so a detection event is, so that's a detection event. During detection time dt, 1 photoelectron was observed or measured or emitted. And that is related to 1 photon was deducted from the light, from the state of the light. So the point is, so that means that during that process, the state of the light changed. There was a state of the light before the detection. There was a state of the light after the detection. Between those 2 states, 1 photon was eaten by the detector. So we had, so if I had state I, that is the state of the light, before the detection. And of course, I could say that F is the state after. Then, and I can ask myself, okay, so what is the probability that one photon was detected, and the light transitioned from this initial state to the final state? So the answer is, okay, tell me what is the probability of having 1 photon deducted from state I and ending up in state F. Now remember, I don't know from which mode this photon was deducted, because I don't know, I have that's the problem. My photodetector sits at some point in space-time. Okay, so it sits there at some point, at some area R in space-time, but it's a small area, it's a small detector. And it is open for a detection time. It doesn't detect a mode, it detects a position in space-time. So if it detected the photo, if there was a photo detection event, I don't know from which mode it was taken out. So I can say that the operator that was operated is this guy. The operator sits at location R and T. It operates on the initial condition. And now if I ask myself what's the probability of ending at the final condition, so this is what happens afterwards. This is the new state. The new state is whatever it was minus a photon. Where in one of those modes? Where is it? I don't know. It's in somewhere I killed one photon. And I'm asking myself, what is the overlap of this with F? So this is the state after detection. And now we do an overlap with the final state. And I ask myself, and I'll take this absolute value squared. Why? Because I want to ask myself, what's the probability of going from state I to state F with a single photo detection event? So this is the probability of transition from state I, from initial to final, while a single photoelectron is detected. So this is this probability. Now, if you want, I don't know if you want, but maybe you want. So this is, yeah, so that would be the probability. Maybe there's a, so, you know, this probability, there could be a proportionality factor here if those states are not exactly normalized, but that's not the important thing. What I want to say is, you know, and then now in many cases, I don't care what the final state is. I want to know what's the probability of detecting a photon independent of where does it end. So this is the probability of detecting a photon and transitioning from I to F. What's about the probability of detecting a photon in state I? So that's the probability of photo detection at initial state I, and disregarding the final state. Well, then it's simple. Then I would say, okay, I don't care which state it will be, so I'll sum over the final states of this, F E plus. Now, let me do a quick trick. So this says, okay, well, if you don't care, then, you know, maybe it's in state F1, F2, F3, sum over all possibilities, and get the final probability to detect to any final state F. Now, I can write this in the following way. Sum over F, what? F E plus I, and here F E minus I. Do you agree with this? trick. All I did was to write the complex conjugate of this. The complex conjugate of this matrix element is the matrix element with the states flipped, and the operator moved to its dagger. Now, E minus is the dagger of E plus. Annoying, as I told you, this is an annoying thing. And now look, this sum over f, ff, is just a unit operator. Right? I mean, this times sum over f, this is just the identity operator. ff times and sum over f. So this equals to I, E minus, E plus, I. So now this is, so if I ask myself, what is the probability of detecting? So now this is an important result. Let me write it to complete. So we can write it here. This P I. So that's the probability equals what? I E minus of R and T, E plus of R and T, I. Now this is something to remember. You remember? So this is like an intensity operator. What's the classical probability of detecting a photon? It's proportional to the intensity at that point in space-time. But the intensity involves both E plus and E minus. Right? It's E times E star. Now the point is that E and E star do not commute. So is it E times E star or E star times E? It depends. And this analysis tells you, look, if you want to detect, to ask yourself what's the probability of detecting, you need to operate with the intensity operator, which measures the intensity of the light. But there's a specific important order. You first annihilate and then create. It should be, I'm saying, it's like asking, I'm going to count photons. What is the intensity? Tell me how many photons are there. Count them. But do I need to do it A dagger A or A dagger? A dagger A will give me N. A dagger will give me N plus 1. Both of them are acting on the same state. So which one is the right one? Which one is the one that will tell me what will I detect? The answer is A dagger A, and not A dagger. Put all the annihilation operators. I know there's a plus here and it's confusing. Remember, the plus, you got used to it. So you first annihilate and then. So for example, if you ask yourself, how many photons will I detect when I put a vacuum state in front of the photodetector? The answer is 0. You'll never see a photon. Why? Well, because you're trying to annihilate a photon from the vacuum, and this knows the state, so this will be 0. But if I put this in front of a 1 photon case, then there will be a detection probability. So this is very similar to having an intensity. So this is like, yeah. The quantum photodetector. So if classically the probability of detection goes like the intensity. The probability of detection in R and T goes like the intensity at R and T, which equals to E times E star. But this one became E plus, and this one became E minus, quantum mechanically. And now it matters which one you put first. So then the quantum mechanical answer is, yeah, you want to calculate indeed the average of this intensity operator, but the relevant intensity operator for photo detection is in normal order. Normal order means you have an equal number of A's and A daggers, and all the A's are on the right side, and all the A daggers are on the left side. So here you'll have E minus times E plus times I. It goes like, and these are, of course, they're dependent on R and T. And this is what we call normal order. Now, as was mentioned, we can talk about generalizing this to coherence function and define quantum coherence functions. We're not going to say much about the quantum coherence function, but we're only going to define it. That is, if you remember the coherence functions. So classically, let's have classical and quantum. Classically, we had gamma 1, which was, let's take only time, okay? So what was it? This was the average of the ensemble average of what? Of E at T1 times E star at T2. This is just in time. Of course, you can do it in space. In space-time, it doesn't, I don't want to carry all those indices all the time. What would be the quantum? And this was an ensemble average over all realizations of the possible correlation between fields at different times or at different locations. Quantum mechanically, this would go to the quantum average. But now we need to say in which order we put them. And you could write E plus E minus, E minus E minus E plus. You could write, I don't know, half the symmetric sum. So there are many possibilities you could write here. So we need to define what, so the answer is we define it at normal order. So we define it E plus on the left of T2 and E minus of T1 like that. Of course, I could have other possibilities, I can write E plus and E minus there are other possibilities. Well, you know what I mean. Other options. Possibilities is too long. Maybe half of E plus E minus plus E minus E plus. All of those could be considered. And it is a convention to use this. Why? Because this one is the one that converges to what the photodetector does. Of course, I could have gamma 2. What was gamma 2? There were many of them. Let's remind ourselves of just one possibility. This was the intensity of T1 times the intensity of T2. Remember that one of the possibilities of the second order coherence was to discuss the intensity correlations between different times or different locations. And now the question is, well, what is this? What could it? Now there could be many possibilities. Here there were just basically one possibility, the other possibility, and then symmetric combination of them. But now there are 4 possibilities. So now there is E plus E minus of T1, and there's E plus E minus of T2. So what will we do? The answer is use the normal order. So that means that we're going to do this. E, there's going to be 4 E's here. And we're going to, and there's going to be an initial state here and initial state there. And here there's going to be twice plus of T1 and T2. And here it's going to be minus. This is 1. Okay. So, good. We have time. This was very general. Let's discuss an example. Let's calculate the first order coherence and the second order coherence of vacuum and a single photon. Okay? So we want to now, example, calculate. So we wrote, we called it gamma 2. Of course, we can sometimes call it G1 and G2. They're called G1 and G2 when they're normalized. So calculate G1 and G2 for a state of vacuum and of 1 photon. Single mode. So we know that there's a single mode. There's only a single mode that is relevant. And we ask about the state of this one. And so So, so I can ask myself, what's the average field? Well, for example, for the case of vacuum, it will be 0 times the electric field operator, and 0. But the electric field operator, what is it? Well, in this case, it's just like doing 0 times A plus A dagger operating on 0. That's the average field. Well, and you know now I can, in one case, I can operate with A to the right and get 0, or I can operate with A dagger to the left. If I'm saying something that you haven't seen or don't know about these tricks with creation and annihilation operators, stop me and tell me. What?
I didn't encounter this trick.
Okay. So, well, you know, I can say that this is 0A 0 plus 0 A dagger 0, right? Now, do you agree that this is 0 by definition? Because A operates on 0 and annihilates it. Now here, if it operates on 0, I get 1. Now you could say then it is killed by orthogonality. So 0 and 1 are orthogonal. That's one thing you could say. Or you could say, well, look, A dagger operating to the right, sorry, A operating to the right is like A dagger operating to the left. Why?
Yeah, because the complex conjugate.
Yeah. I mean, this is so I could say that A annihilates to the right, and that A dagger annihilates to the left. And then, so in any case, however you would like to think about this, this is equal 0. Now, by the way, this is clear. So for vacuum, the average field is 0. What about the average field of a single photon? It's going to be 0 as well, right? Because when I'll write this A plus A dagger will remain the same. But here there will be written 1 and 1. Okay, I will not completely annihilate anything, but the orthogonality will also kill it. So this E is equal to 0 for the vacuum state, but also for the single photon state. So a single photon state has an average field of 0. That's actually correct because it has equal probability of having a plus field and a minus field. So the average field is 0. Now, we need to flip the luach. Now let's ask ourselves, what is the average intensity of the vacuum? And then we can ask ourselves, well, all kinds of other questions, of course. So now I can ask myself, so what is the intensity of the vacuum? So I would like to write the intensity, the average intensity of the vacuum. But when I write this I, okay, so tell me, what do I write here? Okay? Is it E squared? So the question is, okay, so if I ask myself, I can ask, what will a photodetector detect? Okay? So there could be different possibilities. Now that is what would be a photodetection. In the case of the photodetection, the answer is only this: 0, A dagger, A, 0. Why? Because it must be, we write then the intensity in normal order. The only one that is left is this, and this is, of course, 0. So if you put vacuum in front of a photodetector, you will never see any click. But you can ask yourself something else, and that is, what what are the fluctuations of the field, right? I can write, what are the fluctuations of the field? What is this? Delta E squared. What is that? That is E squared minus E average squared. On this you agree? So this is, I'm asking, what's the fluctuation, what's the noise in E of any state? So this is something else. Here I calculate not the intensity. This is not normal order anymore. This average E, we know what it is. This is 0. But this, what is the average of E squared? So this is the average of vacuum. And then what? A plus A dagger times A plus A dagger. Now what's this? Okay, we'll have here A squared plus A dagger A plus A dagger plus A dagger squared. This one will give nothing. This one will give nothing. Well, why operate A twice to the right or operate A dagger twice to the left? Whatever you want, nothing will happen. A dagger A, we already know that gives 0, but this one does not. This one will give 1. So that one, from this only one contribution, that will be 1. Now, of course, this was 1. There are prefactors over there. There's the h bar omega over epsilon v. And then, but eventually, so there is, so the question is there a field in the vacuum?
We saw it. We saw this Gaussian with the,
Yeah,
with the wind.
exactly. So but this is a, so, but remember, this is classically, this is completely impossible. That you will have fluctuations without intensity. Because classically, fluctuations and intensity are the same. If you have fluctuations, then there must be intensity. You cannot have noise with 0 intensity. Quantum mechanically is surprising, it can be done. The fluctuations of the electric field are of the order of 1 photon, although there are no photons. Those are vacuum fluctuations. I think that's nice. By the way, we can do the same and calculate E squared for a single photon. And we'll get that this is, in this case, both A dagger A and A dagger will operate. And this will be 1 times A dagger plus A dagger A operating on 1. This one will yield 1. This one will yield 2. We'll get 3. So that means that the uncertainty of the field for a single photon is of order square root of 3 compared to what? Compared to the vacuum fluctuations. Now, okay. And now let's ask ourselves, what about this? And now about second order coherence. Or this G2 of tau. Now let me remind you, what is it? For a single photon. And then we'll look at the vacuum, but for the vacuum it's not very interesting. So let me remind you of the classical case. Classically, what is the relevant experiment? This is important. What is the relevant experiment? What do? We have light coming in. We have a beam splitter that sends light to detector 1. This one detects the intensity at T1. And here we have, this one detects the intensity of, you know what, of T. This one detects the intensity of T plus tau. And everything is perfect except for the fact that this beam splitter is in the wrong direction. And I cannot see a beam splitter drawn in the wrong direction. If you submit your final homework to me, and there's a beam splitter there, and it's standing in the wrong direction, the outcome is completely unpredictable. No, but okay, so, and we know that classically what is measured is that this G2 of tau equals what? The average of I of t, or I of t plus tau, divided by, normalized to the average of I of, doesn't matter which one, squared. We assume that the average intensity is stationary. Now we want to do this quantum mechanically. Now let's think what happens. We have two detection events. What are we trying to do? We're trying to detect a photon at time t, and also detect a photon at time t plus tau. So this really is, you know, and we said, what does a detector do? It applies first annihilation and then creation. So when we say it measures the intensity, yes, it measures the intensity at the normal order. So that means that quantum mechanically, what will it be? Well, it will be just this one photon here. And here there will be one photon. And then, well, there's this t and t plus tau. So wait, I'm not going to discuss. So this is G2 of tau. We're not going to say anything about tau for now, okay? I want to only calculate for 0 at the same time. So those two are sitting at the same detection. So I'm asking only about, because we didn't define for a single mode, it's not very clear what do we mean by t and t plus tau. Because we don't only have A and A dagger. So what do I really, what am I going to do with time here? There's not really a well-defined time. But I can talk about G2 of 0, tau equals 0. And then there is this 1 here. And then here there's 1. And we said, okay, you operate first with the A's and then with the daggers. Divided by what? A dagger A.
So now tau is 0.
Yeah, exactly. I'm calculating only at tau equals 0. G2 at tau equals 0, and then what is this? Tell me quickly.
0.
Yeah. Do you see it also? You should. And if you don't, then say. Do you see why this is immediately 0? we annihilate twice on a single photon. So the first annihilation will take us to vacuum, and the second annihilation will take us, will nullify it, will annihilate it. So this is, the top is 0. This is 1. What is written here is 1. This counts photons. So yeah, A dagger A operating on 1 gives 1. So for a single photon, G2 of 0 is 0. It actually makes sense, because if there's only one photon here, then this beam splitter is like a coin toss. It's either here or there, in a superposition of possibilities, but still, either here or there. So either this detector will click, or this detector will click, but never both of them. I cannot kill 2 photons out of a single photon. So the probability of doing this, succeeding in annihilating 2 photons out of a single photon, is 0. You can't do that. And this is a quantum result. Because if you remember, G2 of 0 classically is the maximum. And it can never be below 1. Classically, what is written here? I squared divided by I squared. Classically, I mean, the average of I squared divided by the average of I squared. This thing by Cauchy-Schwarz can never be less than 1. It will always be either more than 1 or 1. So this is always larger or equal to 1. And quantum mechanically, we got it 0. So this is a quantum signature. Doing this kind of measurement on some source of light, if you see G2 below 1, you know that what you have is most likely a single photon. If you see it at 0, so if GT2 of 0 is dying to 0, so usually we expect, so we calculated only what happens at tau equals 0. But let me tell you what happens also at different times. So this is the classical case. And this is the classical limit. And it can never go below this. But quantum mechanically, you can have this. For a single photon. So if you have a source of single photons and you do a G2 measurement, the quantum signature will be the fact that you measure G2 and you see that it is below 1. That's already quantum. If it goes down to 0, then you know for sure that you have single photons.
It can also be 1 or above the quantum.
For other states of light, yes. Maybe. So this is a quantum signature for a very specific state, for the single photon state. Let me show you very quickly what will happen if we had here a 2-photon state or an n-photon state. Okay? Because for vacuum you can immediately calculate. Let me just for...
Like the experiment, the mass little energy or something, no?
What? The Hanbury, Brown, and Twiss? Yeah. By the way, the claim against Hanbury, Brown, and Twiss was that how can they measure any intensity correlation if the light intensity is so weak, they only have single photons, they should never see any correlation because they did this calculation. How could you measure 2 clicks when what you have is never more than 1 photon? But that's the point. Weak light is never single photons, even though it's very weak. It always has probabilities of 2 and 3 and 4. Whatever you had in the initial light is only diminished, but the diminish is a constant ratio. The ratio of probabilities remains the same. So, so let me calculate the G2 of 0 for n state. So that's simple. All we're doing is n, a dagger, a, operating on n. And this is divided by n, a dagger, a, n squared. Now, check me. Let's see. This one operating here generates n minus 1. This one operating here generates square root of n minus 1. And then a dagger a counts it. So we'll have n minus 1 squared. Believe me or do the calculation. And if you don't see how to do the calculation, then let me remind you that a operating on n is square root of n times, square root of n times n minus 1. Yeah? And a dagger operating on n here is the same. Oh, I'm sorry, then it's not n minus 1 squared. It's n times n minus 1. That is the same. That is square root of n, n minus 1. So this is what we'll have, and this will be divided by n squared. So you can see that what this is 1 minus 1 over n. So you can see that if you have an n photon state, the result will always be less than 1. But as n goes higher and higher, it is almost 1. I mean, if you have 10,000 photons, you can do a G2 measurement. It's going to be slightly below 1, but it will be very, very hard to notice. So conceptually, G2 measurement is good for any Fock state. But in reality, it is good only primarily for the single photon. It's a good measure to identify the single photon state. The higher states, the deviation from classical becomes small, and very quickly it becomes hard to notice. So to identify a 3-photon state by G2 measurement is hard. But on the other hand, it's also very hard to generate just a pure 3-photon state, so we can forget about it. OK, I think that now is a good time to stop. OK, so we talked about the single mode, and then we talked about quantum coherence, and we talked about G2 measurement and why G2 is considered a quantum signature. And it is indeed a quantum signature for only one specific state, for the single photon. There are other states of light where G2 is useless. And sometimes people use G2 even though it is useless. So it is important between us to identify those cases in order to correct those guys, those poor guys when we meet them. OK, so here we'll stop. Next week, other states, interesting states of light, a little bit about Fock states and why they're very hard to generate, and mostly about other states that are more easy to generate, coherent states and squeezed states. See you next week. מה?
שבמצב של הוואקום...
No, actually, or for the vacuum case, yeah, but it's only because you have a 0 divided by 0. So, but the top part is really 0. So, yeah. Okay. So, say goodbye to you all. And I'm going to annihilate this meeting. And I'm going to turn this off.
הוא לא נראה לי לייב.
מה?
כי הוא לא יודע, לא מצאתי אותו, שבוע שעבר הייתי מהבית.
רגע, אבל מצאת אותנו בפגישה?
אבל ביוטיוב הוא לא הופיע. כאילו הוא עלה עכשיו, הוא עלה...
מה?
הוא עלה מיד אחרי.
היה איזה בעיה בסקייפ?